Hello students, welcome to BTech first year bridge course. In last few lectures, we have discussed about some important aspects in electrostatics. Now today we will start magnetostatics, and in this class we will cover Biot Savart Law and we will discuss divergence of magnetic field. Okay. Now you know that when a steady current passes through a circuit, it produces magnetic fields and that are constant in time. So as a result, the iron filings or iron needles here, which are randomly oriented before the production of magnetic field due to current flow in the circuit, now they are oriented beautifully in concentric circles. So here the direction of orientations of the iron filings indicate the direction of magnetic field, right? So this experiment is a direct proof of production of magnetic field due to current. Now actually this effect was first discovered by Oersted in 1820. Then soon after his discovery, Ampere performed a series of experiments, and from the results of those experiments came out a definite law determining the magnetic field due to a current element, and this law is known as Biot Savart Law. Now according to this law, the magnetic field at a point P here due to a current element IDL is given by this form. So here this R is the vector from the current element to the point of observation, which is P. So here this is called the source point, and the P point where the magnetic field will be found out is called the field point. Okay, and O is the origin. And here mu naught is called the free space permittivity. So for a finite length of current element, we have to integrate over total length of the wire to find out the total magnetic field at P point, right? Now if we consider that the current element has finite cross sectional area, that means it has finite width, then ideal term can be written as JdV. So here in this figure, the n cap ds is the cross sectional area and dV is the volume of this current element. So here dl dot n cap ds is actually will give us the volume of this element, right? So length multiplied by the area is actually volume, you know. So here we use the fact that the volume current density J is parallel to dl, because by definition dl is parallel to the direction of current in it. Okay. So replacing ideal in these equations by J dV, we get magnetic field for a volume distribution of current like this. So this is for a small current element, this form, and this is the magnetic field due to a finite volume distribution of current, right? Now for surface current, the expression of magnetic field will be like this, and here this K is called surface current density. Now here you should note that the magnetic field is function of field point coordinates, and the volume element dV is function of source point coordinates, and R is combination of source point coordinate and field point coordinates. Okay. So later on you will see why we are introducing the concept of source point and field point coordinates, why it is important. Okay. Now you know that using Biot Savart law, one can find magnetic field of different current distributions, right? So for example, one can find magnetic field due to straight current carrying wire, current carrying circular loop, current carrying long solenoid, etc. Right? So these derivations actually you have done in your 12th class, right? So I will not discuss all these derivations in this class. Okay. Rather, we will focus some properties of magnetic field. Now, in order to characterize the magnetic field, you must know its divergence and curl, right? So let's find out the value of divergence of magnetic field. So we know that according to Biot Savart law, the magnetic field at any point due to a volume distribution of current is like this. Now, since the integration is with respect to source point coordinates, we can write by taking divergence with respect to field point coordinates as like this. So here taking the del operator inside the integration is allowed because del operation is with respect to field point coordinates and the integration is over source point coordinates. Okay. Now we have to do this operation. Now let's use these vector identities. So del dot j cross r by r cube is actually r vector by r cube dot curl j minus j dot curl r vector by r cube. And here this curl r vector by r cube is basically 1 by r cube curl r plus gradient 1 by r cube cross r, right? Since this r is of this form, if we operate curl on r, it will give us 0. So it is very easy to prove. You can do. Now gradient 1 by r cube is minus 3 r vector by r to the power 5. So this is simply taking derivative with respect to r, right? Minus 3 r vector by r to the power 5 will come. So here this gradient 1 by r cube cross r, we get minus 3 by r to the power 5 r cross r, right? Now r cross r you know will be 0, right? So here this term is 0, curl r vector by r cube is 0. Now since the current density is with respect to source point coordinate and del operation is with respect to field point coordinate, curl j will be 0, right? So as a whole this divergence j cross r vector by r cube will be 0. Now if we, so here we have that form. So del dot b will be 0. So this is the differential form of magnetostatic Gauss's law. We have discussed about differential form of electrostatic Gauss's law. Now this is the form of differential form of magnetostatic Gauss's law. Now using Gauss's divergence theorem, we get the integral form of magnetostatic Gauss's law. Now let's understand this law physically. Why the divergence of magnetic field or total closed surface integration of magnetic field is 0. Okay. Now here magnetic field lines of bar magnet have been shown. Now you can see the direction of field line is from north pole to south pole outside the bar magnet, and inside the bar magnet, that is from south pole to north pole. So if we consider a closed surface S like this, which forms the volume V, then you can see whatever field lines are going inside this closed surface or this volume, that comes out from the other portion of the closed surface, right? So as a result, resultant flux will be 0, right? So why it is happening? Because whatever field lines is going inside this surface, that is going outside. So resultant flux will be 0. Now what it signifies? It tells that the magnetic lines of force are always closed, right? So you can see magnetic lines of force are always closed. There is no open portion. So magnetic field line is called a solenoidal vector field. It also tells that isolated magnetic monopole or free magnetic charge similar to free electric charge does not exist. Okay, so there does not exist any magnetic monopole. So you will not get a separate S pole or separate N pole. Always you will get the combination of S and N pole. But you can get positive charge separately or negative charge separately, right? So today I am ending here. In the next class we will discuss about curl of magnetic field and from there Ampere's circuital law. Okay, thank you.